Okay, so now the second one is summation of Fy must be equal to 0. Yes? So you will see that by satisfying equilibrium, many different concepts will come about. Okay, and what we are trying to investigate is these concepts. Okay, and from there you would then get the idea of what shear center is, what unsymmetrical bending is, and that sort of thing. So that's where we are getting to. So we have summation of Fy must be equal to 0. That's our second one. So now let's see what happens in the case of Fy. We have all the forces in the y direction must be equal to 0. Okay, and all the forces in the y direction. So what do you get from summation of Fy is equal to 0? What is this? What is the significance of this? Summation of Fy is equal to 0. The significance of this. The significance is that summation of Fy actually gives you the shear. And this summation of Fy is equal to 0 is that equation which you satisfy when you start off any problem by carrying out normal structure analysis. Based on this summation of Fy is equal to 0, you find out your reactions. So this is just a simple equation. So you will use this equation to find out your equation, and then from there you can find out your shear equation. Okay, the shear equation you remember is VQ by IB, and that shear flow. You have read shear flow? Anyway, we will do that over here. So summation of Fy just gives you simple equilibrium equation based on which you find out your reactions. And you will always satisfy that. Why? Because based on that you find out your reactions. Okay, so this will be automatically satisfied. So summation of Fy you will satisfy straight away right from the get-go. Then we have summation of Fz is equal to 0. Okay, there is one thing with the summation of Fy. Summation of Fy within the beam cross section, okay, is equal to tau yx. What is tau yx? Tau yx is the force in y direction on the cross section whose outward drawn normal is in x direction. So in other words, tau yx means that you have got this shear stress which is in the y direction, and it is on which area, which cross section? It is on that cross section where you have the outward drawn normal in the x direction. If you take tau in this direction, that will be tau y z. Why? Because tau y z, because this is the shear on the cross section whose outward drawn normal is in the z direction, and similarly so on and so forth. I mean, like the bottom one, it will be tau y. Okay, no, you can't have the bottom one. So these are the two which you can have. Okay, and this summation of Fy is equal to tau y So along the cross section, your shear is tau yx times dA. Okay, so whatever force you apply on the cross section, that force is taken, this force which you have applied, that will induce some shear stresses in the structure. That shear stresses obviously vary along the length. Along the length it varies. That's why we draw shear force diagram. Shear force diagram is for shear along the longitudinal axis. Okay, but this shear force also vary along the cross section, which is this one. Okay, and tau by x dA, that is the equation for the cross section. So in other words, if I want to find out my shear only in this portion of the area, I will just multiply the tau by x, which is the stress, with this area. Okay, with just this area, and I will get a small portion of shear. And as I go down, the cross section area increases. That cross section will take all my applied load. Do you understand? So this equation tells us that how much area is like the area which is taking the shear force, shear stresses. Okay, now after this we have force in the z direction. Force in the z direction summation of all the forces in the z direction must be equal to 0, and tau zx dA must be equal to 0. Why? Because previously we had V equal to tau yx dA. Why? What was that V showing? That V was for the applied shear load. At every cross section you have got some shear load. That shear load is equal to this tau yx dA. It is that cross section which will take the shear load. So that's why. So in this case we should have tau zx must be equal to 0. So all the tau zx's within the cross section must equate to 0. It is important. If it's not, then what will happen? You can have equilibrium condition, summation of Fz not satisfied. Okay, so you can see that tau zx, because there is no load in this direction, so obviously that is 0 by default. Do you understand? In this case, you had load in this principal direction, so that's why you are getting some value of this. In this direction, you have got no load. So, tau x is equal to 0 in this case. If you apply some load which is in this direction, then you will have this equal to the external at that point. Okay? So this is the forces. We have satisfied the forces. Now let us start with moments. Summation of moment about x-axis must be equal to 0. So what should we do? Summation of moment about x-axis is equal to 0. Remember, summation of moment means the external moment is equal to the internal moment. Okay? So the external moment in the x direction, summation of mx is a torsional moment, isn't it? So so in this case we have that 0. There is no torsional moment. So therefore summation of mx, that is 0 in this case. There is no twisting moment. So we have got so that will be equated to 0. And what is the internal moment? Internal moment is tau yx dA into z. So what I've done is I've taken moment about this origin. We have got this element tau by x dA times z. Okay, which is in this direction. So that will be in this direction, and tau zx dA in that direction. So, and summation of it. Summation of it means that the element which is in over here, the corresponding one. Yeah, you should take the moment of that. Similarly, you should take the corresponding element of this one and corresponding element of that one. They all must equate to 0. If this is not satisfied, then your structure will start twisting. Okay, so this is important that so you can see that this one, the one which is over here, okay, that will have, this one has got y negative and z positives. Okay, and or say, okay, z negative. If we say that this is our first order, z negative. This one, the same area would have y positive and z negative. Okay, so this positive, that positive, negative will cancel, and similarly these two will cancel. So your overall cross section is what is in equilibrium. But what happens if you have a channel section? This is a channel section. Okay? This imagine we have a channel section. Now in the channel section, there are the moment about this point must be equal to 0, isn't it? So we will have some force in this direction, like as we have force in this direction. Okay? So there is tau by x, so force is in this direction, isn't it? So we have some force in this direction, some force in this direction, some force. That's how the shear will flow. The same way the shear flows down over there. So this we will see how this flow occurs. But normally the shear flows either like this or either like this. So see, you can have this time this equal to 0. So there is a couple. These two are causing a couple. This one is causing a moment. So this couple the moment caused by these flow, there is no force which can counteract this moment. What I am saying is that in this case, you could have an element over here and element over here, and they would cause a moment. Okay, and that moment was counteracted by an element in these directions. In this case now, you have got, this is not symmetrical about this y-axis. So you have force in this direction, but there is no force, there is nothing which can counteract that. You have one of this, but this one doesn't exist. Do you understand my point? Look at this one. We have this element in a rectangular section, and this element this element will cause a moment of this time z. Agree? And similarly, this element will cause a moment of this time y. Now you have exactly the same type of element at the top. You add them up, they both come out to be 0. Similarly, you can have a moment, an element over here and an element over here. You sum them up, you will get 0. Okay? Now look at this. You can have element like this, you can have element like this. This one will cause one moment about this point, and that will be counteracted by this one. Okay? You can have an element over here, an element over here. Okay? You can have these two elements, and these two elements can cancel out the effect of each other. But what if you have element over here? There is nothing over here which can cancel the effect. This wasn't the case over here. Why? Because you had symmetry in both the direction. And in this case, you just have symmetry in one direction and not in this direction. As a result, this element will cause a moment. So, how would you counteract that moment? You have to apply the load in a certain direction, at a certain location from this center, in order to counteract this moment. So in other words, you can't just straight away put your load exactly at this point. You will have to apply it in a certain direction, so this moment is counteracted by
moment of that force.
moment of that force. So if I apply load in over here, so that will be counteracted over here. So my applied load must be at some distance from this axis in order to counteract this force, and that distance is called shear center. Shear center. This distance, the distance from the neutral axis where the load is applied to counteract the twisting moment, that is called shear center. So I will repeat what the issue is. In the rectangular section, we have got symmetry in the x direction, in both the axes. In the z axis and in the y axis, we have got symmetry. So no problem over there. We have got a symmetrical section. So if I take an element over here and take the moment about this axis, I will have a similar element in the other direction, okay, and that will cancel the effect. Okay, so if I have got element over here, I can equally take element over there. Respect the signs of the lever arm signs, yeah, and then we will get the moment equal to 0. So rectangular section is a symmetrical section and there is no issue of twisting. The problem comes when you have got symmetry in one axis. If you have got symmetry in one axis, so an element over here and an element over there about the symmetrical axis, they will counteract each other. They will cancel the effect of each other. But about the unsymmetrical axis, which is this one, there is no element to counteract that effect. So if you apply load over here on this cross section on the neutral axis, okay, on the principal plane, if you apply the moment, your section will twist. Why? Because there is no element to counteract the element in your band, to counteract that. So you have to apply load at some distance from the principal axis, which is this axis, at some distance from the principal axis, which is called shear center. You have to apply the load on the shear center in order to overcome that, the twist. So summation of mx is equal to 0, that has to be satisfied. And this we will do in our next class, how the shear center how can we work out the shear center. But I've just given you the philosophy behind the shear center. Okay, so summation of mx is equal to 0. Any question about this one? Okay, so now we go to summation of my is equal to 0. Summation of moment about y-axis must be equal to 0. So y-axis is this one. Okay, it is this one. About y. Initially we had twisting. Okay, so twisting it's like a torsion. It goes like this. Section was like this, it goes like this. Yeah, so straight. In about y-axis, it can go like this. This is about y-axis, isn't it? So it can go like this. So about y-axis, what are the moments which are? What is that force? Tau zx dA. Or which force causes moment about y-axis?
Stress xx dA into g.
Sorry?
Stress xx.
Yes, stress xx about?
Z into z.
Yes, stress xx times z. That is actually the force which caused moment about z-axis and about y-axis. And is there any applied load in the applied moment about y-axis? No, there is no applied moment. So let us write. We have stress xx times dA times z must be equal to 0. 0 because there is no external moment. Now, we said this is Ey by rho. Yes? Agreed? Ey by rho. So, Ey by rho into now again the same thing happens. What can come out of the integral? Integral is dA dependent. So E and rho can come out. Y and Z are dimension of area, so they will stay inside. Okay? So E by rho y z dA must be equal to 0. Now, what is this guy? Y times z dA. Have you ever come across this one? In your engineering mechanics, you have done moment of inertia. You have done first moment of area. And this is something called product moment of area. Product moment of area. What does that mean? You take dA, multiply that with the product of the two variables, y and z. So we have this area, we multiply that with y and z, and that must be equal to 0. The product moment of inertia must be equal to 0. So, in the case of rectangular beam, you can see that by default this thing is satisfied. YZ in this, you take small area, multiply that with YZ, you can find a mirror area over here, you can find a mirror area over there, you can find a mirror area over there, and add them up and you get 0. So that axis where you can do this whole activity of finding out your product moment of area, or that axis which gives you product moment of area 0, that is called principal axis. two are principal axis. Principal axis, these two, do you agree? These two, the y and z, these are the principal axes of our beam, of our rectangular cross section. And for the principal axis, if you take a small area, okay, imagine you divide the cross section into 4 quadrants, yeah, and this is telling you that you take area, okay, anywhere. You take one area over here, the same area, mirror area over there, but with different y and z. Y and z different means different in sign. Similarly, the same dA and different in sign y and z, and similarly over here. Add all of them up, you will get 0. One will cancel. Like this one has got y negative, z negative, isn't it?
Yes, sir.
And this one has got y positive, z positive. So y, so they both will, sum of them is equal to 0. This one has got y negative, z positive, and this one has got y positive and z negative. But both of them, y, z, dA is negative, isn't it? Do you understand my point? So, two negatives and two positives, they will all add up to 0. Agreed? So wherever you can do this sort of activity, where you or those axes which gives you product moment of inertia 0, those are called principal axes. In rectangular, it's the same centroidal axes which are the principal axes. But it becomes tricky. In the case of channel sections, like in the case of sections which have one symmetry, like channel section, it's again the same as the neutral axis. Okay? So in other words, if you take a channel section, okay, this is our channel section, and in the case of channel section, you can have, now let's see, if I take an area over here, can I take, okay, and having, imagine this is my Z and this is my Y. Okay, so I take a section over here and section over there. Would these two cancel out each other? Agreed? Why? Because Z is negative and Y is negative. And in this case, Y is positive and Z is positive. Z is negative. So this one is negative, this one is positive, they both will cancel out. So this is okay. Now come here. If I take this one and this one, this will also cancel out. This one is positive and this one is negative. So this is actually the principal axis. Now let's do it on a purlin, a Z purlin, Z axis. What do you think? We have got an element over here. Is there any element over there? No. We have got an element over there. Is there any element? No. So that means this is not the principal axis. This axis is not principal. So you have to rotate this Okay, you have to rotate this axis. So this axis has to be rotated in such a way that you take an element over there and that has got a mirror element over there with y and z. Do you understand my point?
Yes, sir.
So therefore this will always be at inclination. The principal axis will always be an inclination, and you have to make sure that you apply the load on the principal axis. If you don't apply the load, this won't be zero. So this will start rotating about y-axis. Are you getting the concept?
Yes, sir.
Yes.
Yeah? So this is important. This is very important, that what sort of cross section you choose. You can't just close your eyes and choose one cross section. You must specify for a particular cross section that where should you apply the load. Okay? And that should be the place where all your equilibrium equations are satisfied. So if you apply the load in this case, if you apply the load on these axes in this case, what will happen? This will bend unsymmetrically. So that's where the unsymmetrical bending comes from. Okay? So that will be our topic after shear center. Should I have it up?
Yes.
Now finally, and the last topic of today is the moment about which axis? Which axis? Which is the most easiest? About the Z. Summation of moment about Z axis. Is there external moment in the Z direction? The answer is yes. The moment is always there in the Z direction, isn't it? You always have a moment about, where is the,
So neutral axis, Z axis.
yeah, this is the neutral axis. When you bend the beam, there is always an internal moment, isn't it?
Yes.
That internal moment is actually the flexure moment. The moment in the Z direction is the flexure moment. You draw bending moment and shear force diagram. Those bending moment diagrams, they are the flexure moments, isn't it? Aren't they? So we have moment in the Z direction, just like the shear in the Y direction. We had a shear in the Y direction, and these shears, they cause moments in the Z direction. So M is equal to what will be the moment in the Z direction? Stress xx dA times y. Integral y, and stress xx is this is EY squared by rho dA, and yes, done in MOS 1 that y squared dA, this is actually the second moment of A. So you can also call it as moment of inertia. Okay. So M so M over EI is equal to 1 by rho. You can write. So what does this equation tell us? This equation is telling us first of all, let us refresh our memory about curvatures and radius of curvature. Imagine we have got these two curves. Imagine we take 2 points which are very close to one another, draw tangents to those 2 points, and then draw normal to those 2 regions.